So we are recording now. Good morning, everyone. All right, finally we have somebody in the classroom. Thank you. Okay, great. So yeah, so our goal is to get towards a primal dual algorithm for the minimum cost perfect matching problem for general graphs. So that's the key goal. We will not get there today. We might get there tomorrow. Let's see. But let's first begin with the basics, right? So we want a primal dual algorithm. So we follow the usual recipe. We write down the LP relaxation. Well, we already have the LP, which is the Edmonds LP. We will now call this P henceforth. And we'll write down its dual, which I suggested you do it as a try it yourself problem. And we will write down the complementary slackness conditions and their combinatorial interpretation. Okay. And that will get us started towards the algorithm, but there is a long way to go. Okay. Are there any questions so far regarding Edmonds formulation, the linear program given by Edmonds? Okay. So I'm going to write it down on a new page, and then we'll proceed to write the dual and the CS conditions. Okay. So I need to share a new screen. Give me a second. All right. So can you see the blank page?
Yes, sir.
Thank you. All right. So towards a primal dual algorithm for min cost perfect matching in the general version. So basically, our main interest is non-bipartite graphs, because for bipartite graphs, we already have something which is going to be much simpler than the non-bipartite version. All right. So let us write down Edmonds LP. And from now on, I'll just call this the linear program P. In fact, we may even want to, yeah, I think it's fine. Let's just call it P. And let's call it P subscript G, where G is the given graph. Okay. So during the algorithm, we may be working with derived graphs. So we might need to refer to the primal and the dual with respect to the derived graph. Okay. So given a graph G, the linear program for that is we are minimizing C transpose X as usual, right? Subject to the following constraints. So we have the simplest one. Let's write down the non-negativity constraints. Right, so XC is at least 0 for each edge. We have the degree constraints for every vertex. We want that the summation of the XC values of the edges incident at that vertex is exactly equal to 1. And finally, we have the odd cut constraints, often also known as the odd set constraints, because each odd cut arises from a partition of the vertex set where you have an odd number of vertices on both sides, right? And we are of course going to assume that our graphs have an even number of vertices. So that is saying that for every odd cut, so let's say, so these are non-trivial odd cuts. So script C is the collection of non-trivial odd cuts of the graph G. And for every such cut, we want that the sum of all the variables corresponding to the edges in that cut is at least 1. Okay. Let's just quickly write down what we are going to call these constraints. So these are the degree Sorry, that is non-negativity, my bad. Yeah, these are the non-negativity constraints. These are the degree constraints, and these are the odd cut or the odd set constraints. Okay, I'll generally say odd cut. All right. And now let's write down the dual of this. Okay. So the dual with respect to this linear program for the given graph G is going to be a maximization problem. That part is easy. Okay, so let's see, how do we write down the dual? Anybody has any ideas how to go about this? So how many variables should we have? How many dual variables should we have? Right. We will have a dual variable for each primal constraint. So that will be as many as the number of vertices in the graph and as many plus as many as the number of odd cuts. So that's true. So the number of dual variables is actually going to be cardinality of the vertex set plus the cardinality of the script C set, which is the total number of odd cuts. Okay. Great. So let's call these dual variables. We will represent them by y. So for each vertex, we will have a dual variable yb. And for the odd cut ones, we also will use y, except that let's use capital Y to distinguish them from the other dual variables. Okay. So let's call them capital YD for each element of the script C collection. Okay. All right. So for each vertex, and this is for each D in script C. All right. Okay, so we are going to maximize B transpose Y. What is B over here? If you try to write this as a matrix vector format, what is your vector B? It is just the one vector, right? Because the right hand side is one in both of these types of constraints. Okay, so that part is easy. So it is maximize 1 transpose Y, which basically means we are summing all the Y variables. Okay, maybe I'll just say script C. I don't need to put G. It is clear that we are referring to the graph G in this case. Okay. Okay. Are there any questions at this point? Is everybody happy with the objective function of the dual? Okay. So what are the constraints of the dual? Right. So we have we don't have a matrix vector format written down here, but you can imagine that. What is it? So we have what is the matrix over here? If you think about these constraints, what does the matrix look like? So if I think of this as AX question mark B, right, where some question marks will be equal to and some of them will be greater than equal to. So B is clearly the one vector, that was clear. What is the matrix A? So we have one row per constraint of the primal, right? So we have basically a number of, for each vertex we have one constraint, and for each odd cut we have one constraint, right? So if we transpose this, so let's think about this. So the rows of this matrix we have indexed by the number of vertices in the graph, so and then followed by the odd cuts. And what about the columns of this matrix? The edges of the graph, right? So if we write A transpose, we are going to have the rows indexed by the edges and the columns indexed by the vertices, followed by the odd sets, odd cuts, right? And what will each constraint, if you look at a particular edge, where will you see the ones in that row, in the transpose? So if I look at a specific, so if I consider the transpose matrix and I look at a specific row, where will the ones appear? Anyone in the call? Where should the ones appear for this edge? In which columns? Let's say E is equal to UV. Exactly. So you look at all those columns, which are basically ends of the edge. So you will have a column for U, you will have a column for V. There you will see ones. And then in the script C part of the matrix, you will see ones in all those cuts that contain this specific edge. Right? So all cuts, all odd cuts. I won't keep saying non-trivial. It is clear that I'm referring to non-trivial odd cuts. All odd cuts containing the edge UV. When will a cut contain edge UV? When U belongs to one side and when V belongs to the other side, or vice versa, right? So one of them is in S and one of them is in S bar. Okay. So that is our each, that is what each row of the dual constraint matrix looks like. So for each edge UV, we have a constraint that says that YU, little yu plus little yv plus the sum of all the odd cuts containing the edge E, you take their capital Y variables, okay, and that quantity should be what? So on the, we have a C transpose, so that's what appears on the cost, right? So the cost of the edge appears here. And what is the inequality we get here? Exactly. The variable is non-negative, so it is natural. And so the constraint should be natural. So it should be less than equal to, right? Yeah, exactly. So we have this is less than equal to this, right? So for every edge, you want that the sum of the y variables for the ends of that edge plus sum of all the variables of the cuts that contain that edge, this has to be less than equal to the cost of the edge, right? And let's now think about what are these y variables. So any of them are free variables? If so, which ones? Right. The little y's are free variables. The yv is free for each vertex because that is coming from the equality constraints. However, these are greater than equal to, which for a minimization problem is natural. So the capital Y variables should be natural, which means non-negative. Right? So all the YDs are greater than equal to 0 for all odd cuts. Okay, and that is our dual linear program. Are there any questions or concerns at this point? So I hope everybody is super comfortable with writing duals at this point and that you can follow what we did. If not, please ask right now so that we can resolve it. All right. This is actually very similar to the bipartite one, right? In the bipartite one, we did not have the odd cut constraints. So I will just mark the things which we did not have in the bipartite, right? So we did not have the capital Y variables at all. So we would not have this part, and we will not have this part. If you omit all these things in red, you get exactly the dual for the bipartite version, right? Which makes sense because we have added just some constraints. So we just throw away those variables from our LP dual, and we will get the dual for the bipartite version. Okay, cool. So if you ignore the red stuff, you get the dual for the usual LP, which basically means what we use for the bipartite version, which is not good enough, which is why we introduced these other constraints that was proposed by Edmonds and proved by Edmonds. And that is why we are looking at the corresponding dual. Okay. All right. So what's next? Let us write down the complementary slackness conditions. And I'm going to erase some of the things here, which I hope everybody followed. So let's make some space here. Okay. So let's write down the CS conditions. So we are going to have a primal feasible solution and a dual feasible solution. And we want to write down when these are optimal based on the complementary slackness theorem. So let's say X bar is feasible for P, and instead of writing Y bar, I'm going to write Y bar comma capital Y bar because we have two types of dual variables, right? So the dual solution is the little y variables and also the capital Y variables. So let's say this is a dual feasible solution. And we claim that these are both optimal for the respective LPs if and only if certain conditions hold. Okay, so let's see what are the CS conditions. All right, so let us first look at the CS condition that comes from these constraints. Yeah. So what do we get? Either the constraint holds with equality or yeah. So which variable? The variable corresponding to that edge. Right. Right. So what we get is for each edge UV, I think I'll just write UV instead of the edge E. For each edge UV of the graph G, we have that either the dual constraint holds with equality, either we have YU plus YV plus sum of all the dual variables corresponding to the edges, corresponding to the cuts that contain that edge. So UV belongs to D. Either this is exactly equal to the right hand side, which is the cost of the edge UV, or if this doesn't hold, then we need the corresponding X bar variable to be equal to 0. This is our first CS condition. Okay, so this is, let me make some more space here. Sorry, you are saying the second one? For each UV in the edges of G. Yeah, you're right. Yeah, sorry. What I meant to write is the edge set of the graph G. Yes, is that right? Okay, good. So that's one condition we get. And the second condition we will be getting from this constraint, right? Because the first type of constraints in the primal are equality, so they don't give us any interesting CS conditions. So it is only the inequalities which give us interesting CS conditions, right? So either this constraint holds with equality or the corresponding dual variable will be 0, right? So for each, so this is for each odd cut, non-trivial odd cut, either the constraint in the primal, which is saying that if you sum up all the edges in this cut, this is exactly equal to 1, or otherwise the corresponding dual variable is 0. That will be y bar d equals 0. Okay. So let us try to write down a combinatorial interpretation of these CS conditions. What I mean by that is, let us consider a perfect matching M. So that will correspond to your feasible solution for the primal, and we'll take a dual feasible solution. And we want to know under what conditions will this be a minimum cost perfect matching. We basically want to translate the CS conditions for a perfect matching type of feasible solution. So the combinatorial interpretation is given a graph G with the usual stuff, cost function from the edges of the graph to the reals, and given a perfect matching M and a dual feasible solution y bar comma capital Y bar. If the CS conditions hold for these two, then we know that the perfect matching is one of minimum cost and the dual feasible solution is actually optimal for the dual LP. Right? So let's try to understand what this first condition is saying. So supposing the x bar uv equal to 0 does not hold, that means that the edge is in the perfect matching, right? Because then it will be equal to 1. So whenever the edge uv is in the perfect matching, we need the left hand side condition to hold tightly, right? So the first condition basically says that if an edge uv belongs to the perfect matching M, then the y bar u plus, yeah, I meant to write y bars here, sorry. Yeah, okay. Yeah, then the y bar u plus y bar v plus the sum of all the capital Y bars corresponding to the cuts containing that edge has to be equal to the cost of the edge, right? These are what we generally call as tight edges, right? It's the same idea except that now we have more variables, so we have to deal with them. Right? So whenever this holds with equality, we will refer to them as tight edges. And what this condition is saying is that all the edges of your perfect matching should be tight edges. All tight edges may not be in your perfect matching, but all edges in the perfect matching have to necessarily be tight. And now let's look at the second one. So let's suppose that this right hand side does not hold. So let's say a certain dual variable, a capital Y dual variable, is greater than 0, because remember these are non-negative variables, the capital Y's. So if it is not 0, then it is greater than 0. And in that case, we need that the left hand side holds. And what does the left hand side tell us? So let me write down first. If the dual variable is strictly greater than 0, then can someone translate this for me? What does this really mean? I want to think of it graph theoretically, not in this equation sense. Right? So this is the part I would like you to remember. The X bar is coming from your perfect matching. So it will be an integral solution, right? It will actually be a 0-1 solution. So that's my hint. So given that X bar is a 0-1 solution, can you translate this for me? So what does this mean? If X bar is a 0-1 vector, basically a perfect matching. So what is this constraint really saying? Exactly. If you look at the intersection of M and the cut D, you will have exactly one edge in this cut from the perfect matching. Right? Remember, this is a non-trivial odd cut. So you have to use an odd number of edges in any perfect matching, which could be 1, 3, 5, etc. But this is telling you that the intersection of M and D has to be exactly 1. Does this remind you of something else you have seen before? What is it that it reminds you of? We have seen a similar thing in some earlier problem with primal dual stuff. Does anyone recall? Where have we seen similar constraint? That something intersects with a certain cut in exactly one edge. Shortest paths. Right. In shortest path also we got two conditions. The first condition or the second condition, I don't know how I ordered them. One of them was easy to deal with. So we got an incorrect algorithm, and then to correct it, we introduced directed graphs. So then we got the intersection to be exactly 1. Does everybody recall this? If not, it is a good time to go revisit shortest paths, because you have seen something very similar there. The trouble here is that getting the second condition to hold is very non-trivial, and I have been losing my sleep over that. Okay. Are there any questions or concerns at this point regarding the combinatorial interpretation? So this is the key driving force behind our algorithm. Okay. So as usual, the CS conditions will drive the design of our algorithm. Okay. So this is a good point to ask any questions and clarify anything that is not clear. All right. So let us try to get an algorithm. And I will warn you that although these conditions will drive the design of the algorithm, it is a fairly non-trivial algorithm. And yeah, it's going to take a while. So this was a breakthrough in 1965. It was an open problem for many years. And it is kind of considered to be one of the main contributions that sort of solidified combinatorial optimization as a field of research in its own right. Not something that was tied to other areas, but something that is, worthy of interest in its own right. That is, so yeah. So this was done by Edmonds in 1965. So around the same time, so he came up first, I assume, with the cardinality perfect matching algorithm, and then he solved the cost version using similar ideas, combining it with complementary slackness and those kinds of things. Popularly, it is also known as the Edmonds blossom algorithm, but people typically differentiate them by calling them the cardinality version or the cost version. So let's just call it the cost version. Okay. We won't get there directly. First, I want to take a sort of intuitive approach by considering one of these two CS conditions. Okay. The problem is that we will also need the second CS condition to hold, and that just makes things a lot more non-trivial. I've been trying to find an easier way to do it. I've referred to various books and I've talked to some people I know who are experts in the field, and nobody seems to have an answer. So it seems that the only way to do it is by going through some complicated route. Um, so we will follow CCPS because that seems to be the easiest one to explain without going into a whole 1 or 2 weeks about matching theory. Okay, so let's focus on this condition. Okay. Okay, so let me maybe make a copy of these combinatorial interpretation stuff, and then let's go to the next fresh page. All right. Okay, so here is the idea. So let's just first introduce some terminology, which we have done before, but here we need some more context. So for an edge UV, so given a dual feasible solution, the slack of an edge UV, as usual, is going to be the difference of the right hand side and the left hand side in the dual constraint. So it's a cost minus y bar u minus y bar v minus the sum of all the cuts that contain this edge, and you take the corresponding dual variables. So this quantity we know has to always be greater than equal to 0 because we have a dual feasible solution. When it is equal to 0, we will say that the edge is tight. So UV is tight if the slack is exactly equal to 0. Otherwise, UV is not tight. Okay. And we want a situation where we get a tight graph. So that will be all the edges that will contain only those edges that are tight. And in this tight graph, we want to get a perfect matching, right? So all the edges of the perfect matching will be in particular tight edges. That is the first condition. So let's see how to get there. Okay. Of course, we know that is not enough because we also need the second condition to hold. But let's put that on hold. Okay. So let's go back to what we did in the bipartite case. Let me just quickly remind you what we did in the bipartite case. So we had a recall, and I'm recalling the inefficient algorithm, which we proved that it terminates when the costs are rational. Okay. So I just want to focus on that easier version and see what happened there. So given a dual feasible solution y bar, in that case we did not have the capital y bar variables, and the y bars were basically a variable for each vertex, right? So it was the same stuff, and you just ignore the capital Y bar stuff. Okay. So given a dual feasible solution, we constructed the tight graph H. H is the corresponding tight graph. And in this tight graph, if we got a perfect matching, we knew that that was a minimum cost perfect matching because we only had one complementary slackness condition in the bipartite case, right? And that was the first condition basically. However, if the bipartite graph, the tight graph H, does not have a perfect matching, then we use Hall's theorem. Hall's theorem told us that there is a deficient set, and we use that deficient set to update the dual feasible solution. Right? So if H has a perfect matching, we were done. Otherwise, we apply Hall's theorem. Right? Basically, we run the perfect matching algorithm on H, and it will give us either a perfect matching or a deficient set. So we got a set like this, let's say 3 vertices, and the neighborhood was too small, let's say just 2 vertices. And then the rest of the graph looks something like this. Okay. And all the edges in the graph H, they go like this, they go like this, and like this. In particular, you have no edges going from, as per this drawing, which is different from what I usually draw, you have no edges going from the top left to the bottom right. Okay. But these edges must exist in the graph G, because otherwise G would not have a perfect matching, and we can just run the perfect matching algorithm in the beginning to make sure that our graph has a perfect matching. So in the graph G, we would have these red colored edges, and we use them to update our dual feasible solution. We computed the beta value, and we added the beta to all these guys, and we subtracted the beta from all these guys. Overall, we have added a beta, right? Because overall we have cardinality of S greater than the neighborhood of S. So this is all in graph H, but anyways, it's clear, right? Right, so that's how we updated the dual feasible solution. And then we proceeded, right? So we want to do something similar here. Of course, we can't use Hall's theorem. We have to use Tutte's theorem. Okay. So let's try. So imitating the bipartite case. All right. So we will start with some dual feasible solution. Give me just 1 second. Okay. All right. So let's begin with some dual feasible solution. Can anybody tell me a dual feasible solution? Supposing I give you a graph. Let's say I'll choose some graph. Okay, so here is some graph that I have. We won't use this example in a concrete fashion, but I just want to get some points across. So let's say this is 1, 2, 3. These are the costs of the edges. This is 4, 5, 6, and this is 7, 8, 9. Okay, let's say these are the costs. So can anyone give me a dual feasible solution? Exactly. We are going to imitate the bipartite case as the title suggests. So we are going to put all the capital Y variables to 0 because they just have to be non-negative, so they could very well be 0. And if you put all of them to 0, for the remaining, for the little y variables, you just take the minimum cost of an edge and divide it by half. Right? So in particular, the minimum cost here is 1. So I'll put half on every vertex. Right? And the capital Y bar will be set to the 0 vector. Okay? So this is easy. Set Y bar to 0, and the little y bar, you set it to half times the minimum over all edges. Okay. So we do that, and then we look at the tight graph. So in this example, which I don't want to do concretely, but I'll just do a small part. So in this example, it's very clear, right? The tight graph is simply this graph. I'm not going to label the vertices. There's only one tight edge, and that is this edge. Okay. So this is our current H graph. Okay. Now, this graph doesn't have a perfect matching clearly. So if it doesn't have a perfect matching, then we need to update the dual feasible solution, right? So that part is clear. Until we don't get a tight graph with perfect matchings, we can't even satisfy the first condition, which is what we are focusing on right now. So if H does not have a perfect matching, we definitely need to update, basically improve, if possible, the dual feasible solution. And it has to be possible. If the graph has a perfect matching, we know for sure that there will be some perfect matching and a dual feasible solution that will satisfy the CS conditions. Okay, technically we need to first prove Edmonds perfect matching polytope theorem for that, but we will get an alternative proof through the algorithm, right? So if you assume the theorem, then you know that you should be able to update the Y bar. But we don't need to actually assume it for the algorithm to be correct. The algorithm will give us an additional proof of the same theorem. Okay, so how do we do this? Well, in the bipartite case, we used a deficient set. S was a deficient set. In this case, we have to apply Tutte's theorem. That's where the combinatorial techniques come in. We are using some combinatorial result to understand how to update the dual feasible solution. So, okay, so how do we do this? Use Tutte's theorem. All right. So in fact, you can run the cardinality version of Edmonds' algorithm. It will either give you a perfect matching in H, or it will give you a Tutte set. Right? You will get a frustrated tree, and the white nodes of the frustrated tree will be a Tutte set. Right? So let us suppose we get some Tutte set. Let us say this is my Tutte set. I don't know. Let's call it Z. When we delete the vertices in the set Z in the graph H, we should get more odd components. So let's say we get some 7 odd components. So some of these odd components may have 3 or more vertices, and some of them may have just one vertex. Okay, so I'm drawing them like that. Okay, and I may also get even components. Let me draw them on the top as square boxes. Okay, so just to be clear, these are the non-trivial odd components, where non-trivial means that there are at least 3 vertices in them, and these are the trivial components, which basically means that they are isomorphic to K1 single vertex graphs, and these are our even components. Sorry, all possible subsets of you mean all possible subsets of Z? Uh, no, so we can just look at one touch set, and using that touch set we can try to update the dual feasible solution, right? So there could be lots of touch sets in the graph, but we can run the cardinality version. It will give us one touch set. In the end, we are going to do something much more sophisticated, but at least for now, if we just want the first condition to hold, we can try this naive idea that I am trying to convey, right? So okay, so we get some touch set, and we try to use this touch set to improve the dual feasible solution. And so now let me pose a question. How should we improve the dual feasible solution? We are already at 10:49. Let's take 2-3 minutes to see if anyone can come up with any good answers. Otherwise, we can discuss tomorrow and you can think about it tonight. So let me ask you this, right? We want to add beta and subtract beta. That part is clear, right? Whatever that beta is, we'll find out. So let's say we figure out some beta using some formula. Where should you add it and where should you subtract it? Let me ask that simpler question first. In the end, we want to have a increment, right? Remember when we worked in the bipartite case, we added beta to the S set vertices and we subtracted beta from the N of S set vertices, right? And because cardinality of S was greater than the cardinality of the neighborhood, we overall had an increment, right? It was some K times beta minus K minus 1 times beta. So it is still, we have at least a beta added to the total value of the dual feasible solution. So what should we do here? Where should we add and where should we subtract? Subtract from Z and add to? Exactly. For each odd component, we have an odd cut corresponding to it. For the non-trivial ones, we have the capital Y variables. And for the trivial ones, we have the little y variables, the usual ones, right? And we know that the number of odd components is strictly greater than the cardinality of the touch set Z, right? So we know that the number of odd components of H minus Z is strictly greater than the cardinality of Z. So if we add beta to all of these dual variables and we subtract a certain beta from these dual variables, then we will overall have an increment to the value of the dual solution. That is exactly the idea. Okay, so we will do plus beta for each vertex in Z and minus beta for each odd component of H minus Z. Okay, all right. So again, to reiterate, for the odd components, we may have both kinds of variables, right? So for the trivial ones, you will have the little y variables, and we are subtracting a beta. And sorry, did I make a mistake? I meant to say subtract beta from z and add beta to the odd components. Sorry. I had something in mind and I wrote something else. Right. So we are going to subtract beta for these guys and add beta for these guys, right? So we'll be subtracting 5 times beta in this case, and we will be adding 7 times beta in this case. Okay. And the odd components, either you will have a little y variable, or if the component is non-trivial, then you will be adding to the capital Y variable. Remember, because we are adding beta and those variables are non-negative, we are fine. We are not subtracting from the capital Y variables. Okay. That would be illegal because it could potentially make it negative unless we choose beta carefully. Okay. So now I want you to think about how should you choose beta. Okay. So in the bipartite case, we looked at the red colored edges. So what are the corresponding red colored edges in the non-bipartite graph? Okay. So this is a try it yourself. How should we choose beta? All right. All right. So that's all for today. We will discuss this tomorrow, and then we will think about addressing the second constraint. And in the end, we will need something much more complex than what we are trying right now, but that's fine. My main point today is to just deliver the intuition and why the simple idea does not quite work, but it still gives you some intuition for the more complex things we are going to see later. Okay, so that's all, and I'll see you tomorrow at 9 a.m. If there are any questions or concerns, I'm still here. Anyone in the call has any questions? If not, feel free to leave the meeting. Okay, so I'll stop recording now.